Elon Musk's companies are making a semiconductor bet on a scale normally associated with governments and the world's largest chip makers. SpaceX and Tesla have selected Grimes County, Texas, for the first major phase of Terafab, an advanced semiconductor complex backed by an initial investment of roughly $16.8 billion. The companies say the facility will eventually combine logic chip production, memory, advanced packaging, and testing under one enormous manufacturing system, supplying processors for Tesla's autonomous vehicles and Optimus robots, as well as the computing infrastructure SpaceX expects to deploy for artificial intelligence. If all planned expansion phases are eventually completed, filings indicate investment could rise toward $119 billion. The headline number is extraordinary, but the logic behind the project may be even more important. SpaceX and Tesla are not arguing that existing chip makers have suddenly become unreliable or technologically obsolete. Their argument is that the amount of computing power Musk's companies expect to consume could eventually become too large for the conventional semiconductor supply chain to satisfy on the timetable they want. SpaceX says combined demand from SpaceX and Tesla could exceed 1 terawatt of computing capacity. That is a projection rather than a measurement of today's demand. And whether Musk's companies ultimately reach anything close to that scale will depend on businesses that are themselves still developing, including mass-market autonomous vehicles, humanoid robots, and orbital AI infrastructure. Yet the strategic response is already beginning. Instead of competing indefinitely with every other AI company for manufacturing capacity, Musk wants to build part of the manufacturing base himself. That makes Terafab less like another semiconductor factory and more like an attempt to vertically integrate the physical foundation of Musk's AI ambitions. For decades, the semiconductor industry moved in almost the opposite direction. Building advanced chips became so complicated and expensive that specialization was usually more efficient. Companies such as NVIDIA and many other technology firms concentrated on designing processors, while foundries, led by Taiwan Semiconductor Manufacturing Company, fabricated them. Separate companies supplied memory. Other specialists handled packaging, testing, manufacturing equipment, chemicals, wafers, and hundreds of additional inputs. That division of labor created one of the most sophisticated global supply chains ever assembled. It also created dependencies that become increasingly visible whenever demand suddenly accelerates. Artificial intelligence has done exactly that. The AI boom is consuming advanced logic chips, high bandwidth memory, sophisticated packaging, and data center equipment at a pace that has forced semiconductor companies to increase investment across multiple stages simultaneously. TSMC said in July that it continued to see strong multi-year demand for AI chips while expanding its already enormous American manufacturing commitment in Arizona. Its total planned investment there has risen to roughly $265 billion. The problem is not simply that the world needs more chips. AI needs particular combinations of cutting-edge logic, memory, and packaging capacity, and those combinations cannot be created instantly by adding another factory building. Musk's response is unusually aggressive because Tesla and SpaceX could become consumers of several different types of AI computing at the same time. Tesla autonomous driving strategy depends increasingly on neural network computation, both inside vehicles and in data centers where models are trained. Its Cybercab project would multiply that requirement if autonomous fleets reach large-scale deployment. Optimus creates a second potential source of demand because a mass-produced humanoid robot would require onboard computing while also contributing to demand for training and inference infrastructure elsewhere. SpaceX is adding another layer, After integrating xAI more closely into its corporate structure, the company has promoted the idea of placing large amounts of computing infrastructure in space. That concept remains technically and economically ambitious because orbital data centers would have to solve difficult problems involving energy, thermal management, radiation, communications, and maintenance. But if SpaceX eventually deploys computing systems at the scale Musk describes, semiconductor consumption would no longer be limited to terrestrial data centers. Each business, therefore, points toward the same scarce input, compute. This is the hidden dependency inside the Terafab announcement. Musk controls companies producing rockets, electric vehicles, robot satellites, and AI software, yet many of those products ultimately rely on chips manufactured by companies outside his corporate ecosystem. The more aggressively his businesses expand, the larger that external dependency becomes. In traditional manufacturing, dependence on a supplier is not necessarily a weakness. Buying from specialized producers is often cheaper and more efficient than trying to manufacture everything internally. Semiconductor fabrication makes that argument particularly strong because running a competitive advanced fab requires technical expertise accumulated over decades. Manufacturing yield, equipment calibration, contamination control, process integration, and packaging can determine whether a theoretically advanced chip is commercially useful. Terafab therefore represents a trade-off between specialization and control. Musk appears willing to accept the enormous cost and execution risk of becoming much more involved in manufacturing because the alternative risk is that his companies cannot acquire enough future capacity. His argument has been unusually explicit. Earlier this year, while presenting the Terafab strategy, Musk said the companies face the basic choice: build the project or eventually lack the chips they expect to need. The claim is based on his own projections, which could prove too optimistic, but it reveals how the companies are thinking about the supply chain. Semiconductor capacity is being treated not as something to procure after products succeed, but as infrastructure that has to be built before those products can reach the proposed scale. That reverses the normal sequence. A company ordinarily establishes demand and expands supply in response. Terafab requires Musk's businesses to spend billions of dollars on capacity today because they anticipate extraordinary demand several years from now. If Cybercab, Optimus, xAI, and space-based computing scale as expected, the strategy could look prescient. If those markets develop more slowly, the companies could own an extremely expensive manufacturing system built ahead of actual demand. Semiconductor factories are particularly unforgiving places to make that mistake. A modern fab has huge fixed cost. The economics improve when expensive equipment operates at high utilization and produces large volumes of sellable chips. Underused capacity can quickly become a financial burden because depreciation continues even when demand is weak. Technology also advances rapidly, so equipment purchased for one generation can become less competitive as the industry moves toward newer processes. The ambition of Terafab makes those risks larger. The planned Grimes County site is expected to contain more than 100 million square feet of manufacturing space at full scale, according to the latest project announcement. The first phase alone is expected to generate at least 3,000 jobs, and the project's eventual scale could dwarf conventional industrial developments in the region. Texas officials have promoted it as another step in the state's emergence as a major semiconductor and technology manufacturing center. Yet floor space does not create advanced chips. The real challenge lies inside the clean rooms. Lithography machines must pattern microscopic structures onto wafers. Deposition and etching equipment build and remove material one layer at a time. Inspection systems search for defects that can destroy yields. Advanced packaging connects processors and memory into systems capable of handling AI workloads. Every stage requires highly specialized suppliers and engineers. That is why Terafab cannot become fully independent, even if Musk wants more control of manufacturing. The companies have already turned to Intel. Musk said in April that Terafab planned to use Intel's next generation 14A manufacturing process. The agreement was strategically significant for both sides. For Musk, Intel offers advanced process technology and decades of manufacturing knowledge inside the United States. For Intel, Tesla became a major external customer for 14A at a moment when the chipmaker was trying to prove that its foundry strategy could attract customers beyond Intel's own processor business. That relationship creates one of the most interesting reversals in the story. Terafab is often described as Musk bringing chips in-house, but the project may actually depend on deeper collaboration with established semiconductor companies. Vertical integration does not mean recreating every piece of the global industry from scratch. It means deciding which stages Musk companies want to control directly while building strategic relationships for technology they cannot efficiently reproduce themselves. Intel could become one such partner. Equipment manufacturers such as Applied Materials, Lam Research, and Tokyo Electron could become others. Musk's team has reportedly contacted a broad range of semiconductor suppliers about machinery, substrates, photomasks, testing, and other equipment required for the project. That supplier outreach demonstrates how difficult complete independence would be. Even an enormous integrated fab remains part of an international network of highly specialized technologies. The same applies to memory. AI processors increasingly depend on extremely fast memory systems because moving data can become as important as performing calculations. A processor with enormous theoretical computing capability can still sit underutilized if it cannot receive data quickly enough. High bandwidth memory has therefore become a strategic component of the AI supply chain alongside advanced logic chips and packaging. Terafab's stated ambition to integrate logic and memory manufacturing under one roof addresses that bottleneck directly, but memory manufacturing is itself dominated by companies with decades of accumulated expertise. Building a physical facility is only the first stage. Achieving competitive yields and performance is a different challenge. This distinction matters because Musk is attempting to combine industrial models that the semiconductor industry gradually separated. If it works, integration could reduce coordination problems. Chip architecture, memory, manufacturing, and packaging might be designed more closely around a specific application instead of passing through multiple independent companies. Tesla does not necessarily need a chip optimized for every customer on Earth. It needs processors optimized for its vehicles and robots. SpaceX may eventually want chips designed around the unusual power and reliability requirements of computing in orbit. Purpose-built manufacturing can create advantages when the customer and manufacturer are effectively part of the same system. Apple demonstrated a related principle on the design side by developing custom processors optimized for its own devices. Google built tensor processing units for its data centers. Amazon, Microsoft, and other cloud providers increasingly design custom accelerators to reduce reliance on general-purpose merchant chips. Musk is taking the idea further downstream. Instead of merely designing custom processors and paying an outside foundry to manufacture them, Terafab aims to bring much more of fabrication and packaging into a controlled ecosystem. That could eventually challenge one of the strongest assumptions underlying the AI boom, that NVIDIA, TSMC, and a small group of memory manufacturers will remain unavoidable toll collectors for almost every major expansion in computing. It would be premature to assume Terafab can displace those companies. TSMC's manufacturing scale and process expertise are extraordinarily difficult to reproduce. NVIDIA maintains a powerful combination of hardware and software, and memory manufacturers control technologies that require years of process development. Musk's companies will continue depending on external suppliers for years, even while Terafab develops. The more realistic strategic goal is diversification. If Tesla can manufacture a significant percentage of its future AI processors through Terafab while continuing to use TSMC, Samsung, Intel, or other partners where appropriate, the company becomes less exposed to capacity limitations at any single supplier. SpaceX could follow a similar model. That is particularly important because Musk is not the only executive worried about future chip supply. Meta, Microsoft, Amazon, Google, and other major technology companies are expanding AI infrastructure simultaneously. Semiconductor manufacturers therefore face multiple customers whose capital budgets can reach tens of billions of dollars. Even if global capacity increases substantially, each customer has an incentive to secure a larger guaranteed share before everyone else does. This creates a kind of industrial prisoner's dilemma. Every company fears that competitors will acquire scarce capacity first, so each company signs longer contracts, invests directly in suppliers, or develops custom chips. Those actions encourage semiconductor manufacturers to expand capacity, but they also reinforce expectations that future demand will be enormous. If demand ultimately meets those expectations, the investment looks rational. If it does not, the industry could eventually move from shortage to overcapacity. Semiconductors have gone through this cycle many times. Periods of scarcity encourage aggressive capital expenditure. New fabs take years to arrive, so investment continues while supply remains tight. When those factories finally begin producing, demand may have changed. Prices fall, weaker manufacturers reduce output, and investment slows until the next shortage begins. AI could produce the largest version of that cycle yet because the capital involved is unprecedented. Terafab's potential, $119 billion, full bill figure, illustrates the scale of the wager. That number should not be treated as money already committed or guaranteed to be spent. The current announcement concerns an initial phase of approximately $16.8 billion, and later phases depend on expansion actually occurring. Local agreements themselves contain specific investment commitments that are far smaller than the maximum scenario. SpaceX's signed Grimes County Agreement, for example, commits the company to at least $5 billion of investment by 2030 and at least 1,800 full-time jobs by 2035, while allowing the company to terminate the arrangement with notice. The distinction is essential. A headline saying Terafab could become a $119 billion project describes the upper end of a long-term expansion path, not a check being written today. Semiconductor projects frequently change as technology, demand, and financing evolve. Earlier project filings had also referred to different investment figures as plans developed, which illustrates how fluid the proposal has been. The $16.8 billion first phase is still enormous. More importantly, it creates infrastructure that could make later expansion easier. Once land, utilities, workforce pipelines, and supplier relationships are established, additional fabs can sometimes be added faster than creating a completely new manufacturing ecosystem somewhere else. Texas offers several advantages for that strategy. The state already hosts semiconductor operations from Samsung, Texas Instruments, and other manufacturers, while Tesla has concentrated a growing portion of its industrial footprint there. SpaceX operates major facilities across the state, including Starbase, Bastrop, and McGregor. Tesla moved its headquarters to Texas years ago, and SpaceX relocated its headquarters to Starbase in 2024. Terafab therefore extends an existing geographic concentration rather than creating one from nothing. That concentration can lower coordination costs. Engineers can move between related projects. Suppliers have stronger incentives to locate nearby. Logistics infrastructure becomes specialized around the needs of advanced manufacturing. Universities and technical schools have more reason to build training programs aligned with semiconductor employers, but concentration also creates dependencies of its own. Chip factories require enormous amounts of electricity, water, and specialized infrastructure. Texas has abundant energy resources and has attracted data centers partly because of its power market, yet rapidly growing AI demand is already creating pressure on electrical systems across the country. Terafab would add semiconductor manufacturing to the same regional competition for power that includes AI data centers, industrial plants, and a growing population. Local resistance has also begun appearing around the Grimes County development. Residents have raised concerns about public incentives, environmental impacts, and the scale of industrial development entering a predominantly rural county. Those concerns do not necessarily threaten the project, but they demonstrate another constraint that often disappears from national discussions about reshoring. Washington can decide America needs more factories. Companies can announce billions of dollars in investment. The actual plants still have to exist somewhere, and communities must absorb the roads, workers, water use, construction activity, and environmental consequences that come with them. The incentives offered to Terafab illustrate the competition between regions to secure strategic manufacturing. Texas is providing a $30 million enterprise fund grant, while Grimes County approved substantial local tax incentives tied to the project. Supporters argue that semiconductor manufacturing creates high-paying jobs, expands the tax base, and strengthens a nationally important industry. Critics can reasonably ask how much public support a project controlled by some of the world's most valuable technology companies should receive. That debate mirrors a much broader shift in American economic policy. For several decades, the United States generally allowed semiconductor manufacturing decisions to follow global cost advantages. The result helped create extremely efficient international supply chains, but also contributed to the geographic concentration of advanced manufacturing in East Asia. The politics surrounding chips changed after pandemic shortages, rising tensions with China, and growing concern over Taiwan. Both the federal government and individual states increasingly treat semiconductor capacity as strategic infrastructure. TSMC is expanding dramatically in Arizona. Samsung has invested in Texas. Intel has received government support for its American manufacturing ambitions. Terafab arrives inside this larger attempt to rebuild semiconductor production on U.S. soil. The difference is that Musk is not waiting for national industrial policy to solve his own expected shortage. He is attempting to create a private supply chain solution at enormous scale that could have consequences well beyond Tesla and SpaceX if the project succeeds. Intel's participation is the clearest example. If Terafab helps validate Intel's 14A process with a large external customer, Intel could become more credible as a manufacturing alternative to TSMC. That would matter to Washington because American policymakers have spent years trying to create more advanced foundry capacity inside the United States. Suppliers would benefit as well. A semiconductor complex consuming large volumes of manufacturing equipment, chemicals, wafers, and packaging components could attract additional investment around Texas. Some suppliers might establish local production because shipping critical materials across the world becomes less attractive once a customer of Terafab's proposed scale exists nearby. The chain reaction could therefore look much larger than one factory. Tesla and SpaceX commit capital. Equipment suppliers expand around the site. Intel gains a major foundry customer and has stronger incentives to perfect 14. A specialized labor migrates toward Texas. Packaging and material companies establish nearby capacity. The cost of building another semiconductor project in the region gradually falls because parts of the ecosystem already exist. That is how industrial clusters become self-reinforcing. The same process helped Taiwan become dominant in semiconductor manufacturing and helped Silicon Valley become dominant in technology. Once suppliers, workers, customers, and capital concentrate geographically, each new investment becomes easier to justify. Terafab is essentially betting that an equivalent feedback loop can be accelerated deliberately in Texas. There is no guarantee it will work. The strongest counter-argument is execution. Elon Musk has a record of pushing manufacturing projects at speeds established industries often consider unrealistic, and that approach produced significant achievements in electric vehicles and reusable rockets. Semiconductor fabrication, however, has its own constraints. A rocket can fail visibly, and the engineering team can redesign it. A semiconductor process can suffer from subtle yield problems across hundreds of manufacturing steps, turning a technically functioning factory into an economically disastrous one. Leading-edge chipmaking rewards repetition, statistical control, and incremental process refinement. TSMC's advantage is not simply that it owns expensive machines. It has spent decades learning how to coordinate those machines at enormous volume while achieving the yields customers require. Terafab will have to acquire that capability somehow. Intel can provide technology and expertise, and other suppliers can provide world-class tools, but the project still has to integrate everything into a production system capable of competing economically with mature manufacturers. That is why the first chips coming out of Terafab will not be the most important milestone. Yield will matter. Cost per functional chip will matter. Reliability will matter. Production volume will matter. The speed at which the facility can transition to newer process generations will matter even more. If Musk's companies simply manufacture expensive chips internally that could have been purchased more cheaply elsewhere, vertical integration becomes an ideological achievement rather than an economic one. For Terafab to change the industry, control has to create an advantage large enough to compensate for the enormous cost of building it. That advantage could come from customization. Tesla can design silicon specifically for autonomous driving and robotics rather than optimizing for a general external market. SpaceX could create processors tailored for orbital AI systems. Manufacturing and product engineers could work together more closely than they can through a conventional customer-foundry relationship. Another advantage could be guaranteed demand. Most new foundries have to convince external customers to trust an unproven manufacturing process. Terafab begins with potential captive customers in Tesla, SpaceX, and the broader Musk ecosystem. If those businesses actually grow according to plan, utilization could be supported internally before the fab ever needs to compete broadly for third-party customers. This is similar to how vertical integration protected Tesla during earlier phases of the electric vehicle industry. The company invested aggressively in battery systems, software, charging infrastructure, and manufacturing because Musk believed dependence on conventional automotive suppliers would constrain the product he wanted to build. Terafab applies the same philosophy to silicon. The difference is scale. A $16.8 billion initial commitment puts the project immediately among the largest industrial investments in the country. A full build approaching $119 billion would move it into an entirely different category, comparable to the largest semiconductor expansion programs anywhere in the world. That scale reflects how dramatically the meaning of manufacturing is changing in the AI era. For much of the internet economy, the most valuable companies could scale software to millions of customers without building correspondingly large amounts of physical infrastructure themselves. AI reverses part of that model. Better models increasingly require massive amounts of computation, and computation requires chips, power, cooling, networking, and physical facilities. Software companies are becoming infrastructure companies. Infrastructure companies are becoming energy companies. And in Musk's case, companies that began with cars and rockets are now preparing to become semiconductor manufacturers. That transformation may be the deeper story behind Terafab. The AI race is moving upstream. At first, competition centered on who could develop the best model. Then the focus expanded toward who could obtain the most GPUs. Companies responded by developing custom accelerators. Now the competition is reaching the factories that manufacture those accelerators. If future AI demand becomes as large as Musk expects, access to semiconductor capacity itself becomes a strategic asset. SpaceX and Tesla are effectively buying an option on that future. The initial $16.8 billion pays for more than a factory. It buys the possibility that several years from now, Musk's companies will not have to ask an outside foundry for enough capacity to support millions of autonomous vehicles, millions of robots, and a potentially enormous AI computing network. Whether those businesses become large enough to justify Terafab remains uncertain. That uncertainty cannot be separated from the project. Optimus is not yet a mature mass market product. Fully autonomous cybercab operations still have to prove themselves at enormous scale. Space-based AI computing remains a highly ambitious concept. A projection of more than 1 terawatt of future computing demand assumes that several difficult technological and commercial bets succeed simultaneously. If they do, today's semiconductor supply chain may indeed be too small for Musk's ambitions. If they do not, Terafab could become an enormous monument to demand that arrive more slowly than expected. That is why the project is much more interesting than a simple reshoring story. SpaceX and Tesla are not spending $16.8 billion because America suddenly ran out of chips this week. They are spending it because Musk believes the future demand curve is moving faster than the supply curve, and he does not want the growth of his companies determined by whether someone else's factory has capacity available. The investment therefore begins with a forecast. From that forecast comes a factory. From the factory could come a new Texas semiconductor cluster, a major opportunity for Intel, new demand for American semiconductor suppliers, and a partial reshaping of the global AI hardware chain. Or the forecast could prove too aggressive, leaving expensive capacity competing against companies that have spent decades perfecting semiconductor manufacturing. Both outcomes remain possible. The distinction will not be settled by the size of the groundbreaking announcement, the number of square feet in the plans, or even the amount of capital ultimately spent. It will be settled by whether Tesla and SpaceX create enough real demand to keep the fabs running, and whether Terafab can turn that demand into competitive chips at scale. For decades, companies like Tesla and SpaceX could outsource one of the most technically difficult parts of their future to the global semiconductor industry. Musk is now betting that the next phase of AI will make that arrangement too restrictive. The world's chip makers are already spending enormous sums to expand, and TSMC itself says AI demand remains strong for years. Yet Musk's conclusion appears to be that even those expansions may not arrive fast enough for what his companies want to build. That is why $16.8 billion is only the opening number. Terafab is ultimately a wager that computing demand will become so large that owning the factory producing the chips will be almost as strategically important as owning the AI models, robots, vehicles, and satellites that consume them. If Musk is right, Texas is not simply getting another semiconductor plant. It is getting a new piece of the infrastructure on which several of his companies are betting their future.